Hello, my dear children of class 11 science. Today we again to continue with the chapter stationary superposition of stationary waves number 2, and basically we are dealing with stationary wave, or also called standing wave, and the vibration of air columns. Okay. Now today we complete this chapter. Now we basically start today's class with one of the last topic from this chapter. Okay, that we basically deal with the mode of vibration of air column in open organ pipe. So in the last class, we discussed the mode of vibration of air column in closed organ pipe. Okay. Similarly, now we discuss in today's class with the mode of vibration of air column in open organ pipe. So with this topic, okay, so we'll complete this this particular chapter, superposition of waves. Now, organ pipe, as you can basically classify into two types. One is called closed organ pipe, another is called open organ pipe. Okay. Now, what is open organ pipe? Now, open organ pipe is simply like a tube, a long cylindrical tube. Okay, is a cylindrical tube which is open at both ends. Which is open at what? Both ends are usually called open organ pipes. That means a cylindrical tube which is open at both ends is called open organ pipe. Now, this organ pipe is also used as a musical instrument. This organ pipe is also used as a what instrument? Musical instrument, okay, and can produce the note of different frequencies. The note of different frequency means the vibration of air column, the vibration air particle present in the pipe can be made to vibrate in different modes, and these modes can lead to the sound of different frequency. Sound of what? Different frequency. And children, you learn in the last topic, that is in closed organ pipe, the sound of vibration of air column in the pipe made the vibration make the sound to produce with different frequency, and basically what frequency we saw? The odd harmonics. Now in today's class, with this particular organ pipe, we see what mode of vibration can be observed, okay, and what type of frequency can be observed under open organ pipe. So for this we consider a pipe, pipe of length L. So we take a pipe of length what? L, open at both ends, and this pipe is lying along x-axis. Lying on what axis? X-axis. Which means we take a long cylindrical tube which is nothing but a pipe which is open at both ends. So I am taking this as a pipe, and this pipe is lying on x-axis. Lying on the which axis? X-axis, whose one end, say I consider x is 0, okay, and other end is x equals to L. So that the total length of the pipe is how much? The total length of the pipe is how much? L. So what is the length of the organ pipe? L. This length is L. Okay. Now sound can be made to produce from any of the end. We can make the sound to produce from this end also. We can make the sound to produce from this end also. Okay. Because both ends are open. Okay. So that you can produce the sound from any of the end. Okay. So what happens when we blow? When we what? Blow air at its end. Say I consider the when we blow air at its end at x equals to 0. That means when you blow air from this end. So you are blowing air from this end. What type of wave it produces? A longitudinal what? Sound wave will produces. And this sound wave is produced by the vibration of air particles present inside the pipe. Okay. And this longitudinal sound wave travels in the air in the pipe towards the end x equals to L. That means sound wave propagate in this direction from x equals to 0 to x equals to what? L. Okay. Now this wave will get reflected okay, back. And when this get reflected back, okay, when get reflected back, the two wave, one is the wave which is called incident wave, longitudinal wave, traveling from x equals to 0 to x equals to L, get reflected back and get reflected and produce a reflected wave. And this reflected wave produces from x equals to L to x equals to 0. But as I said, in case of this open organ pipe, the sound can be produced from any of the end, either from x equals 0 to x equals to L. But only thing is that the wave, that is called longitudinal wave, can travel, okay, by the vibration of air particle present in the pipe, okay. So that the two waves, one is called incident wave and reflected wave, they always superimpose each other. They get superimpose each other and always form a what wave? Stationary wave. So what type of wave generate inside this long open organ pipe? Stationary wave. And due to this stationary wave, The sound of vibration give you a frequency. Sound of vibration produce a sound of certain frequency, and this frequency of the vibrating medium of the air particle of the open organ pipe lead to the sound of different frequencies. Okay, lead to the different frequency. But as I said, the pipe is open at both ends. Both ends are open. So usually what happens? There is always an antinote formed at each end. So open end always has form what note? Antinote. So in case of open organ pipe, children, remember this: whether you produce sound from this end to this end, or whether you produce sound from x equals L to x equals 0, but sound produce okay and reach to this end always make the particle to vibrate with maximum displacement. So that's why the antinote is always formed at both the ends. Antinote is always formed at both the ends under any mode of what? Vibration. Okay. Now to calculate the different mode of vibration, to observe different mode of vibration, and with this different mode of vibration we measure the sound of different frequency. Okay. So let's start with the first mode of vibration. Let's start with the what? First mode of vibration. Now in case of first mode of vibration, we take the same pipe, the pipe whose end one end is x equals to 0, another is x equals to L, so that the total length is what? L. Okay. Now we make the sound to produce from this end in such a way so that there will be one antinote is formed at this end, and there is another antinote is formed at this end. But between these two antinote, one note will form between this end. I consider somewhere at this point. Only at this point. So forming two antinote always at the open end, and one note which is formed between the two end. Okay, between the two end leads to the sound of a definite frequency, a particular frequency, and this frequency is also called fundamental frequency. And this vibration is called first mode of what? Vibration. So in first mode of vibration, also sound produced with a certain wavelength, and that wavelength I consider as lambda 1. So lambda 1 be the what? I consider lambda 1 be the wavelength. It is the wavelength of the what? Standing wave. So it is the wavelength of the what wave? Standing wave. Okay. Set up in the air column. In the what column? Air column. Okay. Under this mode of vibration. So if wavelength, certain wavelength is set up in this mode of vibration, then definitely we have can measure the first mode of vibration. But as I said, in first mode of vibration there will be antinote at the end, and only one note is formed between the end. So your frequency, your mode of vibration looks like this. So let me draw the diagram. Okay, so your diagram goes like this. Yes. Now you see, this is the mode of vibration takes place. First mode of vibration, and this is what? Note. Note and antinote. Note is always formed at the middle of this pipe, where antinote is formed at the open end of the pipe. So this mode of vibration is called first mode of what? Vibration. This mode is called what? First mode of vibration. Under this mode also we can measure this length. This length can be measured in terms of this wavelength. To measure this one, so we just follow the relation that since L equals to, there, see, one is antinote, there is note. And you know, between note and antinote, the distance between antinote and note is always given by lambda by 4. But what is the wavelength I consider? Lambda 1. So distance between antinote and note, see, this distance is lambda 1 by 4. Plus there is another distance that we can measure between note and antinote, and that distance also what? Lambda 1 by what? 4. See, antinote and note distance lambda 1 by 4, antinote and note distance lambda 1 by 4, which means L equals to lambda 1 by 4 plus lambda 1 by 4. Okay, so if you take LCM, so LCM will be 4. Okay, if the LCM is 4, then it will be lambda 1 plus lambda 1 means 2 lambda 1. Now we can divide this, 2 1s are 2, 2 2s are what? 4, which means L equals to lambda 1 by what? 2. So if L equals to lambda 1 by 2, then we can just cross multiply that lambda 1 equals to 2L. See, lambda 1 equals to 2L. The wavelength of the standing wave under this mode of vibration will be 2L, double the length of this pipe. Okay, so L equals to lambda 1 by 2 means lambda 1 equals to 2L. So with this wavelength, we can measure now the frequency of mode of vibration. So I write down, let nu 1. So I am writing with nu 1. But children, as you know, the frequency symbol can be expressed by N also. So but I writing with the symbol nu 1. Nu. So nu 1 be the what? This one, nu 1 be the frequency. This is the frequency of, okay, what? First mode of vibration. First mode of vibration. So if nu 1 is the first frequency of first mode of vibration, then you know frequency is equals to speed by wavelength, and outer I am writing again speed of this wave is called b. So small letter b is the what? Be the speed of the wave. The speed of wave. So nu 1 frequency equals to speed by wavelength. Therefore, this nu 1 equals to speed by, now you know what is lambda 1? Lambda 1 is 2L. Lambda 1 is how much? 2L. So you can see now the frequency of first mode of vibration. Okay, that means nu 1 is coming as B by 2L. B by what? 2L. And this particular frequency is the lowest frequency of the vibration. And this frequency is also called fundamental frequency. Okay, so this is the what? This is the lowest frequency. Let me write it down. This is the lowest frequency. Okay, and we call this lowest frequency as fundamental frequency. Fundamental what? Frequency. Fundamental frequency of the what column? Air column. Because what is actually vibrating? Air column. Okay, and this, under this particular case, the sound note which produced in the pipe is also called fundamental tone. So under this case, I write down the sound note. The sound note, okay, produce, sound note what? Produce in the what? Pipe, okay, is called, what we call, this is called fundamental. So I am using the word fundamental tone. Fundamental what? Tone also we call as first harmonic. We use the word called first harmonic. So this is the case which is observed in the open organ pipe. But this case basically arises in the pipe when air is blown lightly at the end of the what pipe. That means when you blow air lightly in the end of this open organ pipe, then we get the sound of frequency which is called fundamental frequency, and we get the sound of note produced in the pipe called fundamental tone or first harmonic. And this mode of vibration is called first mode of what? Vibration. Okay. Now similarly we can go to the next mode of vibration, that is called second mode of vibration. So let me come to now the second, okay, mode of vibration. Now we do with second mode of what? Vibration. The second mode of vibration can also be observed in a similar manner, but under this mode we make the sound to vibrate, okay, in such a way so that there will be antinote which is formed at the two ends, because both ends are opened. One is antinote, another is also antinote. But between two antinote there will be two note which is also formed. Between what? There will be two note which is also formed. So let me mark somewhere out here. There will be a note and there will be a note which is formed. Okay. So note and note also will be formed. So this will be the note and this will be also what? Note. Okay. So your vibration, mode of vibration of a column basically observed under this case is called second mode of vibration. And this second mode of vibration, in this second mode of vibration, as I said, there are what? Two antinotes at the two end, okay, but additional two note which is formed between that, and one antinote is also formed at the center. There is one more note which is formed at the center, that is called antinote. So between two antinote, two note and antinote which is formed leads to the formation of second mode of vibration. This is the vibration, mode of what? Second mode of vibration. Now this can be observed again with the diagram. So let me draw the diagram of this mode of vibration. Okay, so under this mode of vibration, your diagram looks like this. Okay, I'm drawing this way. And this way, it goes this way. Yes, now look at the diagram. This is called second mode of vibration because the end which are open where the particle have a maximum displacement, okay, starting at both end. But when we come to the end where I have marked by letter N, this is node where the particle has minimum displacement, no displacement. Okay, again when it goes to other end where there is antinode where the particle has maximum displacement, and node particle has minimum displacement, and antinode where particle has maximum displacement. So the nature of the mode of vibration looks like this. And this mode of vibration is called second mode of vibration under open organ pipe. So under this mode of vibration also we can measure the wavelength and we measure the what? Frequency. And the wavelength of this second mode of vibration I consider as lambda 2. So lambda 2 be the wavelength of the standing wave under this second mode of vibration. And to express this wavelength in terms of the length, again I do in the similar manner, since your L, the length of the organ pipe can be calculated in the similar manner. Now see, between antinode and node, this is, the distance is always what? Lambda by 4. So it will be lambda 2 by 4 plus, again between antinode and node, see antinode and node distance, again lambda 2 by 4. Between this antinode and node, again lambda 2 by what? 4. And lastly, between this node and antinode also, distance is lambda 2 by what? 4. Okay. So now we take the LCM of denominator, and the LCM is 4. 4, LCM is 4. So but how many times this is adding? 1, 2, 3, 4 times. It will be 4 lambda 2. So now see the factor in which we have calculated is L equals to 4 lambda 2 by what? 4. Let me just divide by 2, 2 are 4, 2 2 are 4, which means L equals to 2 lambda 2 by what? 2. Now if I cross multiply, it will be 2L equals to 2 lambda 2. Okay, 2L equals to 2 lambda 2, which means lambda 2 equals to 2L by 2. See, I'm not dividing this, cancelling this 2 and 2 because I just want to follow the sequence. Because in the first mode of vibration, your wavelength was how much? Lambda 1. And lambda 1 was what? 2L. This is 2L. That means this 2L means actually lambda 1. So which means if this is lambda 1, then lambda 2 is half of lambda 1. Lambda 2 is what? Half of lambda 1. So I can write this way also. Lambda 1 by 2. Because this 2L means what? Lambda 1. So we can easily understand from this mode of vibration that the wavelength of this mode of vibration, that is lambda 2, is half of the wavelength of the first mode of what? Vibration. So corresponding to this wavelength, we can calculate the frequency. So I write down the frequency. The frequency is basic marked by letter nu2, and this frequency means speed, travel with the same speed b only, and wavelength is lambda 2. Okay, which means b, I write down b by lambda 2. So lambda 2 is how much? 2L by what? 2. Okay, let me just put the value. Lambda 2 means 2L by what? 2. Which means this will be reciprocal 2B by what? 2L. 2B by what? 2L. Now what is B by 2L? See children, B by 2L is nu1. So I replace this by nu1. Which means the frequency of second mode of vibration, that is nu2, is 2 times the frequency of first mode of vibration. The frequency is 2 times the first mode of what? Vibration. So under second mode of vibration in open organ pipe, the frequency of second mode of vibration is twice the second frequency of first mode of what? Vibration. So children, under this mode of vibration, you can see the frequency that we measured is called twice the first mode of frequency of first mode of vibration. That is also called fundamental frequency, which means under this mode of vibration, when the sound is produced, the sound note which produced in the pipe is called which tone? First overtone. This tone is called first overtone, and we also call as what? Harmonic, second harmonic. So in open organ pipe, okay, we are getting what? even harmonic, not odd harmonic. Where in case of closed organ pipe, we got the what? Odd harmonic. Whereas this is second harmonic means the even harmonic. And the tone which is called false overtone. Now this way, the second mode of vibration has been calculated. So similarly, we can check with the next mode of vibration, and then we can see the sequence. Now under this mode, that is called third mode of vibration, we take the same organ pipe with the same length, having one end x equals 0, other end x equals to L. And you know, in open organ pipe, and both end open, always there is a what? Antinote is formed, okay, at both end. But in this mode of vibration, that is called third mode of vibration, other than these two antinote, there will be three note. So how many note? Three note, and two antinote is formed between this note. Between these two antinote, there will be three note which will form, and two antinote is formed. Because in the second mode of vibration, you know, between antinotes, two notes and one antinote has formed. Now this is next mode of vibration. That means there will be how many? Three antinote is formed, and two note is formed. Three note is formed, and three antinotes are formed. Two antinotes are formed. Sorry. So this will be note. Again, there will be antinote. There will be a note. There will be a what? Antinote, and there will be a note which is formed. So as I said already, under this mode of vibration, between two antinotes at the two end, three notes are formed and two antinotes are formed. Okay. So with this, your sequence, your wave disturbance will be looks like this. So your disturbance looks like this. Start this way. Okay. So let me draw in this manner. With this note, this antinote, and this. Again this note, this antinote, note, antinote, and this. So this is the disturbance that is produces. Yes. So if you look at the diagram, children, so antinote, note, antinote, note, this is note, antinote, maximum displacement, note, minimum displacement, antinote. So this is the nature of mode of vibration occurs inside the what? Open organ pipe. So under this mode of vibration also we measure the wavelength and the frequency. So under this case, I consider lambda 3 as you know, symbol lambda 3 with the wavelength of the standing wave. So as the lambda 3 is the wavelength of standing wave, then this length, again this length L, can be written the same way, but I do directly like this also. So just look at it. I can do this way also. We can measure this length as there is antinote, antinote. You know, distance between two antinote is lambda 3 by what? 2. Antinote node distance lambda by 4. Again antinote distance and node distance is lambda by 4, but antinote distance will be lambda by 2. That's why it is lambda 3. I have considered lambda 3 wavelength by 2. Plus again antinote distance what? Lambda 3 by what? 2. Plus again antinote distance is what? Lambda 3 by 2. So we can do this way also. Instead of adding antinote node like that, we can add antinote, and antinote. Okay. Now it will be how much? LCM is 2. So it will be how much? 3 lambda 3 by 2. Because lambda 3, if you add, it will be 3 lambda 3 by 2. So we can write now this as lambda 3 equals to how much? 2L by what? 3. So under this mode of vibration, children, that lambda 3 that we got as how much? 2L by what? 3. How much? 2L by what? 3. So this is the wavelength of the standing wave under this mode of vibration. In this mode of vibration, okay, which measure the wavelength, also measure the frequency. And I write down the frequency. Okay, under this mode of vibration, under third mode of vibration, we are calculating under third mode of what? Vibration. Okay, and that frequency, yes, we can mark by letter nu 3. And frequency means speed by wavelength, and wavelength is how much? Lambda 3. Okay, so let me just put the value B by lambda 3 is how much? 2L by what? 3. So nu 3 equals to, now 3 will go up, 3b by what? 2l. Okay, now what is b by 2l? Actually this is what? Nu 1. So nu 3, the frequency is third mode of vibration is 3 times the frequency of what? First mode of what? Vibration. First mode of what? Vibration. That means nu 3 equals to what? 3 times the first mode of what? Vibration. That means the frequency of third mode of vibration is 3 times the frequency of first mode of vibration. So under this case, the sound note which produced in the pipe will be the second overtone. Second overtone, also called third harmonic. So I write down. Under this mode of vibration, the sound note, okay, produce, okay, in the pipe is actually called second overtone. We call as what? Second overtone, or also called as third harmonic. Third what? Harmonic. So just following the sequence, if I go for next mode of vibration also, from here it is clear that the frequency of the fundamental tone and the overtone of an open organ pipe, this will be under the ratio, and this ratio will be what? Both odd and even harmonic. That means open organ pipe produces a frequency of both harmonics, odd harmonic also and even harmonic also. So children, we can make a conclusion, okay, and the conclusion under this open organ pipe is the frequency of the fundamental tone, also called fundamental frequency, and the overtone of an open organ pipe that we have already calculated, nu 1 is to nu 2 is to nu 3, the frequency ratio is 1 is to 2 is to 3, it will go on and on. So what mean this? This means the open organ pipe can produce both the harmonic, so both the harmonic, even harmonic and odd harmonic. Whereas you saw that in case of closed organ pipe, the closed organ pipe produces the frequency only of odd harmonic, whereas open organ pipe produces the frequency of all the harmonic, even and odd harmonic. Therefore, from here I can even make a conclusion that any musical sound which is produced by the musical instrument made up of open organ pipe is richer than the musical sound produced by closed organ pipe. Because in open organ pipe, you can get any of the harmonic, whether you want to get odd harmonic or even harmonic, both are present. Whereas in case of closed organ pipe, you saw that the odd even harmonic are always missing, whereas only we get what? Odd harmonic. Okay, that's why to use open organ pipe as a musical sound, okay, it is better to use what? Open organ pipe than the closed organ pipe. Because in open organ pipe, we get both the harmonic. All the harmonic are present. Okay, so these are the detailed explanation of the mode of vibration of air column in open organ pipe. Now children, we will solve few numerical problem, okay, based on this chapter, okay, from this chapter, and the chapter get completed. So we do continue next YouTube video with the numerical problem from this chapter.